A geometric sequence is defined recursively by specifying values of a sub 1, which is non-zero, and the equation a sub n over a sub n minus 1 is equal r, where r is also non-zero. We can, however, find the formula for the nth term of such sequence, and the theorem listed here gives such formula. It says that if a sub n is a geometric sequence with the first term a sub 1 and the common ratio r, then a sub n is a sub 1 times r to the power n minus 1 for any n greater or equal 1. The theorem also gives us the formula for the sum of the first n terms of a geometric sequence. That formula depends on the value of r. If r is equal 1, the sum is n times a sub 1. If r is different than 1, the sum is a sub 1 times 1 minus r to the power n over 1 minus r. Let's justify these formulas briefly. So the first one, that a sub n is a sub 1 times r to the power n minus 1, this formula comes simply from the definition. We know that a sub n over a sub n minus 1 is equal r, so a sub n is a sub n minus 1 times r. And this means that if you choose a sub 2 is going to be a sub 1 times r. If we use n equal 3, we'll have a sub 3 is equal a sub 2 times r. But a sub 2 is computed just right here. It's a sub 1 times r. So if we substitute a sub 2 with a sub 1 times r, we'll get a sub 1 times r squared. If you compute a sub 4, then a sub 4 is going to be a sub 3 times r. And again, we substitute a sub 3 by the formula that we just obtained, will give us that this is a sub 1 times r to the third. So you can see that the values of that sequence, the terms of that sequence, all have the a sub 1 and all are multiplied by r to some power, and the power is 1 less than the index of the term. So we have a sub n is a sub 1 times r to the power that is 1 less than the index we are using in the term a sub n. As for the second formula, we'll consider first the case when r is equal 1. If r is equal 1, that from the above we know that a sub n will be always a sub 1 times 1 to the power n minus 1, and since that is 1, it's going to be always a sub 1. So any term of that sequence is always an a sub 1. It means we have a constant sequence. So if we add a sub 1 plus a sub 2 plus a sub n, we're really adding a sub 1 n times, so that's going to be n times a sub 1. Now if r is not 1, then we'll denote by s that sum. This is a sub 1 plus a sub 2 plus and so on plus a sub n. So we can write using the first part that a sub 2 is a sub 1 times r. Then we'll have a sub 2 times r, a sub 1, a sub 1 of course, r squared plus and so on. Then we'll write the term a sub n minus 1, which will be a sub 1 r to the power n minus 2. And finally term a sub n, which will be a sub 1 times r to the power n minus 1. Now let's multiply that sum by r. So we're multiplying r by s. What will we get? We'll get a sub 1 times r plus the second term multiplied by r will give me a sub 1 r squared. Then we'll have a sub 1 r cubed. And we continue. The second to last term will be a sub 1 r to the power n minus 1 and a sub 1 r to the power n if we multiply. We'll subtract now those equations side by side. So the left-hand side is going to be s minus r times s. And what will happen on the right-hand side? Since we'll be subtracting bottom equation from the top, you can see that we have a sub 1r in both of them. They will cancel out. We'll have a sub 1r squared. They will cancel out. And so on. A sub 1r minus 1 will cancel out with a sub 1 r to the power n minus 1 on the top. So what will be left on the right-hand side is just a sub 1 from the top equation and minus a sub 1 r to the power n from the bottom. We'll factor out s from the left-hand side and we'll have 1 minus r, and we'll factor a sub 1 from the right-hand side and we'll have 1 minus r to the n. And dividing by 1 minus r, since r is different than 1, this is non-zero number, will give us that the sum is a sub 1, 1 minus r to the power n over 1 minus r, which is the right-hand side of the formula that appears in the theorem.